We are witnessing a technical reversal in the way software is built. As AI coding tools become more advanced, the environment they prefer to operate in is returning to a previous state, the text-only interface. There is a growing contrast between how humans and machines navigate code. Human developers rely on integrated development environments, or IDEs, which use spatial mapping and visual cues to manage complexity. A machine, however, processes code as a raw data stream, making the headless environment of a command line interface far more efficient. This shift is being driven by a new generation of autonomous agents, including tools like Codex, systems like Claude Code, and agents like Klein. When these agents are constrained within standard IDE plugins, their performance often degrades. They struggle to maintain state across multiple open tabs or lose focus during complex refactoring tasks. Yet, when these same agents are deployed as headless processes in a terminal, they operate with a level of speed and precision that would overwhelm a human observer. This suggests that the visual interfaces we designed to help humans manage information have become an architectural bottleneck for machine logic. To understand why machines are retreating from the graphical layer, we have to look at the software stack itself. At the base, we have APIs for system communication. On top of that, an SDK, or software development kit, packages the libraries and compilers needed to target a specific platform. The next layer is the command line interface. The CLI wraps the SDK, exposing its internal operations as scriptable text commands. The IDE sits at the very top of this pipeline. It integrates the SDK and CLI into a single workspace, adding buttons, menus, and visual overlays to make the underlying tools accessible to a human user. But the machine doesn't need the buttons. Crucial security protocols, like the SIG-v4 cryptographic signing used by AWS, happen automatically at the lower layers. The system evaluates credentials based on a strict priority matrix that moves from the CLI environment variables down to the container level. Operational logic is also handled at the base. When a cloud endpoint hits a rate limit, the SDK layer manages the recovery through exponential backoff, retrying the request automatically without the developer ever seeing an error message. This entire pipeline was engineered to shield humans from complexity, but in doing so, it obscures the raw data that an AI agent is designed to parse directly. The way AI interacts with this stack has evolved through 3 eras. It began with Era 1, reactive, inline autocomplete features that predicted the next few characters as a developer typed. Era 2 introduced the chat sidebar. This required a human to serve as a manual bridge, copying code from a chat window and pasting it into the editor. Now we have reached Era 3, autonomous agents. The AI doesn't just suggest code, it plans the implementation, edits files, and runs the tests itself. When Era 3 agents try to operate within an IDE, they encounter a problem called context pollution. A modern IDE is constantly processing background information, diagnostic states, UI logs, and the contents of every open tab. In a visual environment, all of this data is forced into the LLM's active memory at once, creating noise that degrades the quality of its responses. The CLI avoids this through a method called progressive disclosure. Instead of receiving everything at once, the agent uses targeted search queries, like grep or find, to extract only the specific code and context it needs for the task at hand. By stripping away the visual overhead, the agent preserves its memory for logic rather than interface data. Headless text environments aren't just a preference, they are the optimal operating space for machine reasoning. There is also the issue of the feedback loop. In a chat-based IDE, the AI is effectively blind. It doesn't know if its code works until a human manually runs a build and reports the results. In a terminal environment, the feedback loop is automated. When a command executes and fails, it generates standard error logs that the machine can read directly. CLI native agents parse these standard exit codes to diagnose a failure instantly. They generate a patch and trigger a new execution command in a continuous cycle, without any human input. This autonomous cycle is supported by a standardized bridge, the Model Context Protocol, or MCP. MCP servers act as plugins that allow an agent to securely reach outside its local environment. Through a single protocol, a CLI agent can connect to external databases, project management tools, and deployment pipelines. This allows tools like Codex to run as long-running MCP processes, exposing their memory and toolsets directly to the environment where the code is executing. This integration transforms the CLI from a simple input window into a fully integrated execution environment for autonomous machines. Even with an automated loop, a single agent can struggle to manage a massive codebase. Without oversight, a lone model can lose track of project-wide dependencies or introduce regressions in unrelated modules. To solve this, developers use agent SDKs to coordinate specialized teams. In this workflow, a central project manager agent acts as a gatekeeper for a team of specialized designer, developer, and tester agents. The project manager enforces structural gating. It reviews requirements and blocks any handoffs until the necessary file artifacts are created, ensuring the team remains aligned with the project's architecture. Once the developer agent completes a task, the payload moves to the tester agent. The tester runs the diagnostic suite against the original requirements and reports the outcome back to the project manager for final validation. This entire process is monitored via an agent tracing dashboard. It records every tool call, file edit, and execution duration, providing the audit trail needed to debug and optimize the multi-agent pipeline. Coordinating agents within these structured CLI pipelines provides the verification framework needed to produce reliable code at an enterprise scale. Despite the efficiency of the CLI for autonomous agents, the IDE remains necessary for human engineers. Visual workspaces are still the best way for humans to understand high-level architectural changes that span multiple systems. Likewise, evaluating user experience requires a visual canvas. Only a human can accurately judge how a layout renders in a browser or how a design feels to a user. IDEs also act as essential compliance gates. They provide the visual diff tools humans need to review agent-generated pull requests before they are committed to the codebase. This creates a hybrid workflow where ad hoc automation starts in the CLI and eventually matures into the robust SDK architectures managed within a studio environment. We are seeing a division of labor in software engineering. The underlying execution layer is moving back to the headless CLI, leaving the IDE to function as a high-level oversight dashboard for human review.